Okay, welcome to today's lecture. So this is lecture 8 of the electrodynamics course. I'm sorry I can't be there live today, but we'll do our best to manage everything with these short videos. The idea of today is that we're going to discuss magnetostatics in matter. So this is a direct continuation of everything we've done with electrostatics. It's going to look relatively similar, but of course with some important differences. One recommendation which I have for you is really to pick up this wonderful book by Purcell-Morin and eat through all of chapter 11. It contains a lot of real physical information about this subject matter. Here we sometimes go a little bit deeper in some of the technicalities here, but the Purcell-Morin is going to give you a very, very solid basis from which to understand absolutely everything that's happening here. So very, very highly recommended. I'll also keep these videos quite short, so you have the time to work through the details really by yourself quite a lot and to read through Purcell-Morin. So what is this about? Well, we've discussed magnetic fields quite extensively up to now in the absence of matter. And one of the things that we did was discuss the multipole expansion of the magnetic field, because as we explained, if you're a certain distance from a source of a magnetic field, the most important term, the leading term in a 1/distance expansion is the dipole term. We encountered the notion of magnetic dipoles, which you can think of in your head as tiny little loops of current. We argued that the important aspect, the important characteristic of this is their magnetic moment, which is in a sense the surface average of the normal vector to that with the multiplied by the current that goes around it. So we had this little magnetic moment M associated to a current loop. Here we're using a very, very simple cartoon of this, which is just a tiny little surface surrounded by a current I going through in this case a counterclockwise direction, therefore representing a magnetic moment M pointing out of the page here. So it's just worthwhile to state a couple of basic physical facts about such current loops. First of all, what happens to them if they themselves are based in an external magnetic field, here represented by the blue arrow B? Well, okay, let's just see how it goes. You remember the Lorentz force law. It just tells you that charges in motion in a magnetic field encounter a force. So in this case here, we've got 4 contributions to the force to this loop. So let's take it chunk by chunk. Maybe we take this chunk first. By just using the right-hand rule, you can see that for each chunk, we have a force which is perpendicular to both the current itself and the magnetic field. So here, the magnetic field I view really along the z-axis, if you want, going straight up. So in this case, for this part of the loop, the force is going to be in the x direction like this. So the forces are just represented by these orange arrows that you have in here. The point is that this particular force is going to be counterbalanced by the force on the opposite side of the loop here. And here I imagine that my loop is kind of tilted a certain angle as compared to the z-axis. So these two ends here have forces which directly counterbalance each other. However, the other two sides, so this one here and the one on the top, they also have a force which is going either in the positive or the negative y-axis. But taken as a rigid object here, that means that there's actually a torque being operated on this surface. The torque being just the moment of force around this rotation axis, which in this case would be the x-axis. So if you just look and think a little bit about your right-hand rule, you will realize that the torque, which is as usual a vector, is given by the cross product between the magnetic moment and the external field. Okay, so this is like a super idealized representation of what a magnetic dipole is, but the relationship of the external field, the magnetic moment, and the resulting torque is given by this very simple relation that you've got here. So what this means physically is that in the end, magnetic dipoles tend to align with the magnetic field. If they're free to rotate, if they're free to kind of move around a bit, they will somehow try to move in a direction to minimize the energy, and that means just putting themselves in line with the field. Okay, now very briefly, another thing to quickly mention is that although the resulting force vector on the full object is 0, so it's not because there's a torque that the thing would start drifting, moving around. If the external field is not uniform, so if the magnetic field actually depends on position, then it could be that there's a resulting drifting force on the dipole. And this this resulting force would then depend on the differential of the field in the direction, for example, here in this case, in the Z direction, or even in the other directions. So in the case of a non-uniform field, you can actually look at the details of what the force is, and what it is just a gradient of m dotted into b. So here I would like to refer to Purcell-Morin section 8.4, because there are really wonderful illustrations of what that is, and calculations also for a simple case showing you how to get this formula here. Okay, but this is just some formula that you can know exists and refer to if you ever need it. Okay, so this is the kind of very basic notion of physical forces